Newton's third law states that when one object, we'll call it object 1, exerts a force on a second object, we'll call it object 2, the second object also exerts a force on the first object. These two forces exerted by the two objects are equal in magnitude and opposite in direction, giving the forces together the name action-reaction pairs. So if I were to draw this out, we would draw this out as the contact force, so F sub c of 1 on 2, and it has the same magnitude but the opposite direction, so the same length of arrow but opposite direction, as the contact force of object 2 on object 1. So these two forces exist simultaneously. It's not as if the action force causes the reaction force at a later time. They both exist at the same time. So take the example of a horse pulling a cart. So there's a force that the horse exerts on the cart. So if we were to look up here, the force that the horse exerts on the cart, so this again is a contact force of the horse on the cart. We'll call that, if we call that the action force, so we'll label this action. Then the reaction force is the force that the cart exerts on the horse. So the horse is pulling the cart forward, and likewise the cart pulls back on the horse, and that's what the horse feels, which makes it difficult to pull the cart. So we call this one the reaction, since we called the first one the action force. Now, the force that you call action and which one you call reaction is totally arbitrary. Usually the first one you think of, you just label that the action force, and then that makes the second one the reaction force. We could have just as easily labeled it the other way. So we write for these forces, if now we're going to write it an equation, we could write here that the force, the contact force of the horse on the cart is equal to the negative the contact force of the cart on the horse. So they have the same magnitude, but they are opposite in direction. So in the above example, we write the forces with the subscripts object A on object B, horse on cart, cart on horse. So you can see which object exerts and which object experiences the force. So one reason that we recommend the subscript in your notation is that it makes it much easier to recognize third law pair forces or action-reaction forces because they have the same two objects, H and C, in their subscripts, but they are just in opposite positions in the subscript. They switch positions, so horse on cart versus cart on horse. Now I want to mention a common mistake with action-reaction forces is to think that action-reaction forces act on the same object. But notice here that that's not the case with all of our action-reaction forces, because the on for this one is on the cart, but the on for the action-reaction force is on the horse. Same thing with object 1 and object 2. These are action-reaction pairs, but the first one we drew here is on object 2. The second force that we drew here was on object 1. So action-reaction forces always occur on different objects. That means that these forces can't cancel each other out, and motion can occur because they're never going to end up on the same free body diagram since they don't act on the same object. So we'll discuss this further in the tutorial. Forces, the other really important thing to know about third law pair forces is that they can only be third law pair forces if they're the same type of force, because one has to be a reaction to the other, and the reaction is going to have the same form as the original force. So for example, a surface may exert two kinds of forces if a block slides on it. You might have, for example, a block that is sliding along a table. So if the block, say, is sliding in this direction, then we can draw some different forces that exist. We'd have, of course, we have the normal force of the table that is pushing up on the block. And then the third law pair force here would be the normal force, so same type of force, of the block on the table. Now there's another kind of force that's exerted between the table and the block in this case, and that's the frictional force. So since the block is moving to the right, The frictional force, this is a force of kinetic friction that's slowing down the sliding. So the frictional force of the table on the block is to the left to slow it down. And in reaction, the frictional force, there's a frictional force that's exerted, this is an F, between the block and the table by the block on the table. So these are third law pairs. If they're the same color here, this is a third law pair. And these on this side are third law pairs. Same type of force, same two objects, but in different positions. Notice that the frictional force of the block on the table and the normal force of the table on the block, these are not third law pairs, even though we have the two same objects in the subscript and they're reversed in position. Since a frictional force is different than a normal force, these are not an action and reaction to each other, so these are not a third law pair.